So our first speaker for this session is Manuel, who is the CEO of Tau Systems. And this is going to be some really big physics tech. So take it away, Manuel.
Thank you, Will. Pleasure to be here, pleasure to opening the second session here. And yes, it's going to be really big physics, doesn't get any bigger, literally. Show you in a second. So what we do is we, at Tau Systems, and we spun this out of my laboratories at UT Austin 2 years ago, we shrink particle accelerators. And you may be forgiven for thinking, why? Well, if you think about the first computer, it was a building-sized machine. And today, we got this. And the big transformation that brought is you use it for way more things than the first computer was ever invented or indeed envisioned. And we think we can do the same thing with particle accelerators. They have a lot of use cases, and I am personally convinced most of them haven't even been thought of and invented yet. But this is your largest particle accelerator in the world. This is CERN in Switzerland and France. Actually, about a quarter is in Switzerland, the rest is underneath France. It's the largest machine we have ever built as a species. It's 27 kilometers in circumference and has cost several $1 billion, just the accelerator, and then another 10 billion or so for the detectors. And it is a fascinating machine. I remember when I was an undergrad student, I got to visit CERN and I was blown away. If you're a physicist, this is like a cathedral. And it's fantastic, but then you learn what it takes to actually run these things. And the paper on the Higgs boson and from 2012 has 5,154 co-authors. And I realized, okay, I can go into this, but as a grad student, you're only ever going to see a tiny, tiny part of the whole picture. You can work on the theory, you can work on the physics, you can work on detectors, on accelerator technology, but you only ever work on a tiny, small part. And that wasn't for me. I was interested in all of that. And so I started thinking as a grad student, well, is there a way to make them smaller? And and before we get to making them smaller, CERN actually wants to make it bigger. This is the plans for the future circular collider, which is 100 kilometers circumference. And right now, not that it's approved or anything, but cautious estimates put it at about 50 billion euros. Which means before you build the thing, it's going to be 3 times that. So I doubt that this will ever happen unless, and there's fantastic physics to be done with it, so unless we come up with a different technology that makes this significantly smaller and cheaper. And so I said, as an undergrad even, I started looking around, are there any ideas how we could possibly do that? And I found this paper written in 1979, so when I was 6, by John Dawson and Toshi Tajima. They are on that paper there, and I regret to say I never got to meet John Dawson because he passed away in 2001, but Toshi Tajima is a good friend and colleague and multiple co-author with me by now, and we've really worked a lot together since. But the basic idea of this paper was you can build a laser electron accelerator, and in a normal accelerator, you get an accelerating field of about 10 megavolt per meter. And if you want to accelerate something to 100 GeV, like CERN did at the time, you need 10,000 meters to do it. Add in bending magnets, diagnostics, all kinds of technology, you end up with 27 kilometers of the ring. A laser wake-field accelerator can get a field of 100 GeV, 100 gigavolt, 100 million gigawatts, 100 billion gigawatts, 100 GeV per meter. So 10,000 times stronger than this, which means your accelerator can be 10,000 times shorter than this, 1 meter. Get the same energy in 1 meter. Well, that was great. That was what I was looking for. Problem was, this is a theory paper. And there was no laser at the time that stood within a prayer of ever achieving this. Couldn't be done. Until Gerard Moreau and Donna Strickland at the University of Rochester invented something called chirp pulse amplification. Wonderful method to make very, very powerful laser pulses. And again, I'm honored to know and work with Donna. She's here at visiting our group at UT. Donna is only the second woman after Marie Curie, 115 years later, to get a Nobel Prize in physics. Now, I'm also very glad that since then, 2018, we had two more, Andrea Getz and Yuli, just last year. But I mean, tremendous, tremendous person, wonderful to work with. Anyway, the idea here is, the problem with amplifying very, very strong laser pulses is they are very, very short, just a few femtoseconds. And power is energy divided by time, so even with very little energy, they are very powerful. And damage threshold of optics is a function of power. So as you start amplifying them, you immediately start damaging all your laser materials. Not good. So the idea was, well, we can stretch it in time. We can give it a chirp. We can have the red part of the spectrum come first, then the yellow, then the green, followed by the blue. And then we amplify it. Now it's long, the power is low. Then we amplify it, and we expand it, and then we compress it again, and you end up with a very high power pulse. And very high power for the lasers we are using means on the order of 1 petawatt peak. That is 1,000 times the installed electrical power in the United States for a very short moment in time. So now we have our laser, and how can we use that to accelerate particles? Well, the limit we have to overcome in a conventional particle accelerator is basically the material threshold of the metal, copper, niobium. And this gives you this 10 megavolt, 10,000 volt per meter. And if you go above that, you damage the metal. Now, the laser, now we have the laser, and we have a laser that can produce our field of 100 gigawatt per meter. And, but we still damage the metal if we do that, so we need something else. And the something else we need is a plasma. Instead of accelerating particles in metal, we accelerate it in a plasma. Plasma is the fourth state of matter. You start with solid, you heat it up, you get liquid, you melt it, you heat it up further, you vaporize it, you have a gas, you heat it up further, you rip off all the electrons from the atoms, and you have a plasma. Once you've done that, what else are you going to do to it? You can't damage it anymore. So we can put this tremendously strong field in a plasma and use this to now accelerate electrons. Other particles, but mostly we do electrons. And this works basically like surfing. The electrons surf behind a plasma wave, like wake surfers in a boat. So we got this cell. This is our accelerator cell. It's about 10 centimeters long. Here we let in helium. We have a small laser that creates nanoparticles to seed our electrons. They get taken up by the helium and evenly distributed through that whole volume here. And so we now have our cell filled with helium and metallic nanoparticles. And when this has equilibrated nicely, we shoot the petawatt laser. And it's like a laser bullet. It's very small, width of a hair across and also width of a hair long. And that laser pulse, though, as I said, it's a petawatt. It's 10 to the 19 watts per square centimeter, and it ionizes the gas, creates a plasma, and creates this plasma wave that it draws behind it, like a boat creating a wake that it draws behind it. And like people can surf on that wave, the electrons can surf on that plasma wave, and they get drawn along, and they get immediately accelerated to the speed of light in just a few millimeters, centimeters, depending on how high we want to get the energy. And so we end up with a very high current, very, very short electron bunch at very high energies that we can now go and use for something. And just to show, I wanted to bring the plasma cell. This is the actual plasma cell. I can literally hold it in my hand. I can't bring it because we're using it right now. It's in the laser, it's being used. But anyway, this is it. And from that plasma cell, we got the same energy than SLAC down the road gets in 2.5 miles, 10 GeV. So we showed that actually works. And so we can use this to build small particle accelerators that are tailored to specific applications. And we can tailor them to one application per machine, because unlike CERN or SLAC, it doesn't cost $10 billion to build one, it costs $10 million to build one. So that's great. What do we do with it? Well, I said, there's a plethora of applications. The first one, and this is the one we are actually now starting to commercialize, where we have first customers, is radiation testing for electronics that go into space. And we've heard a lot about computer chips and how they're going to be speeding up and how fast they're going to be. They already are, and they're going to get even faster. Well, if you want to put it in space, unfortunately, you are stuck with something that is somewhat slower than a Pentium 3. Because in space it sees radiation, you have to radiation harden it. That's difficult, and you have to test for that. And the only place you can test in the US is Brookhaven National Laboratory and Berkeley National Laboratory, two very large accelerators that together supply an amount of test time of a few hundred hours a year, when there is a demand between government agencies and industry of about 30,000 hours a year. So we figured, okay, that's a good point for us to start. And we have a strategic collaboration with NASA, Jet Propulsion Lab, and Aerospace Corp. And we basically have our prototype machine in Austin. That's it. It's maybe, so that's the laser here. That's maybe the size of the stage. That's the test beam line, maybe another times the size of the stage. It makes an electron beam. The blue points here are data from the Berkeley Heavy Ion Accelerator. Those points here are ours. We can not only linearly scale to these points and cross-calibrate, we can extend the parameter space by a factor 3. And we just did, this is fresh, this is hot off the press, we just did this last week. This is the academic prototype at UT Austin. We are right now building a more engineered and refined version in our new facility in Karlsbad. We basically have the right part of this building here, 25,000 square feet, but it's not just the machine, it's offices, it's other lab space and so on. So you could put one machine into about 4,000 square feet. This is the plans, this is the clean room. The clean room is in now, we're installing the laser. And that laser is going to be 100 times more powerful than the one we have at UT Austin. Shoots 100 times a second, the one in Austin only once per second. So this will already enable routine production line testing for customers. Another very interesting application, and we're working on that, this is still kind of in the academic level right now, we're working on this with colleagues from MD Anderson, is something that's called very high electron energy therapy, cancer therapy. You can use this to irradiate tumors, and if you go to very high electron energies, you can do this very efficiently, just as efficient as with a big proton machine. The problem is to get to those high energies with an electron accelerator, you're building a huge machine again. Unless you use ours, which is small, and now you can build 10 of those machines for the price and size of one proton machine. And so very exciting, but of course, medical, irradiating people, there are a little longer development times there. So we'll go slowly here, but we have actually the first experiments, not on people, on phantoms, starting this fall. Another very cool medical application together with Sean Zhang from UC Irvine is an X-ray imaging. It's actually not, it's X-ray acoustic tomographic imaging. If you have a very, very short burst of X-rays, or for that matter electrons, and you send it into some tissue, it will launch a shock wave. Now that sounds worse than it is. What I'm talking about is a sound wave. So you can surround that tissue with ultrasound microphones, and due to the pulse being very located, it has different flight times to the different microphones, and in one shot you can assemble a complete 3D image that in a standard CT will take you a few hundred shots. So that means you can get a good 3D image, but you can reduce the radiation dose compared to a CT by a factor 100 or so. So that's already pretty cool, because now it means you can use that as routine screening. Breast cancer is one of the applications they are looking at. We men don't have to feel left out. Prostate cancer is the other. the really cool thing comes when you combine the two, because the electron pulse that we would use to do the therapy is also very short. It would also launch a sound wave like that. And we could do not just the irradiation, we could do real live monitoring of what dose are you depositing where, and you could basically tailor a perfect treatment profile. And that gets us to another application, and this is one we're also looking at very, very hard, because that's actually many applications. We already heard about Moore's law and how we want to extend it or put a wall up or break it or whatever. But what I am convinced of, no matter where we go as a species, we will find and we will try to find some way to keep this going. We'll have to, there's the need. One way, of course, is to keep shrinking transistors. Another way is to start 3D packaging different structures. And then, of course, far off maybe, but there's, well, maybe not so far off, quantum computing on silicon, single atom-sized elements, who knows? But if you want to mass produce them, right now there's at least some of these things get assembled atom by atom with an atomic force microscope, not very friendly for mass production. So we think our machine can help with these things. And here, for example, is an X-ray image of a standard micron memory chip that we just did the other week. And the cool thing here is we get a broad spectrum of X-ray. We can do hyperspatial imaging. We can look with different detectors in different layers. We can do one-shot 3D imaging with this. And in this case, I'm blown away because this is the best picture we ever did, but I'm also disappointed because we are resolution limited. We have a 1 pixel resolution limit here. If I get a better detector, we can drop the resolution on this image another factor 30 and get submicron, which for this whole stacking and packaging will be really relevant. Now then, can we do lithography? Yes, ultimately. And we can do it in a way that really enables going smaller. We can use our electron bunch to build an X-ray laser, soft X-ray laser. And the way you do this, it's called a free electron laser, and SLAC down the road has one, only it's 2.5 miles long. But we can use that same principle and shrink it down and make it fit here on that stage here, basically. And what you do is you take this electron bunch that we have, right? We take our electron bunch and send it through a few magnets and beam conditioning systems, and then we send it into something called an undulator, which is an array of permanent magnets, North Pole, South Pole, North Pole, South Pole, North Pole, South Pole, and the electrons start to wiggle in that undulator. Well, this is why it's called an undulator or a wiggler. Every time they wiggle, they emit light. The light they emit is a function of their energy, so we can tune it. And if you set it all up right, the emittance of light will give a little recoil to the electron. And so some of them will slow down, some of them will speed up. And they order themselves into these nanosheets, into these very ordered nanosheets. And when that happens, now they're all in phase. Now they all emit coherently. Now you get a laser. And you get very, very, very bright, brilliant emittance at a tunable wavelength. The current EUV source is 13.5 nanometers, and there's nothing you can do about it because it's an atomic line of tin. Here, we can build a EUV source that we can run at 13.5, but we could run it at 12.8 where we get better optics, or we could run it at 6.7 where we get a factor 2 in resolution, or we could run it at 4.4 nanometers carbon K-edge where we may be able to make use of other substrate properties and a factor 3 in resolution. So we think this is a way for a next generation lithography machine that really allows us to go to the angstrom limit. And when we have that technology, and we have actually a prototype up here in Berkeley together, it's a joint project with Lawrence Berkeley Laboratory. It's not in the EUV yet, but it is lasing visible blue light right now. And over the next years, we're going to tune that down. And you can see the system. I mean, it's a room, but it's not a campus. So hopefully, because with tunable wavelength, right, we have a knob on the resolution, we can really bring this down to where, and offer one way to keep Moore's law going. So we're headquartered in Austin. We have the collaboration up in Berkeley. We're building our facility in Carlsbad. We have about 23 people right now. We started with 15 million seed funding. We're raising the next round right now. We're also hiring. If you know any good mechanical engineers, control systems engineers, please send them my way. And ultimately, this is, if we put everything together, we get 10 GeV electrons, like we already get out of the accelerator, with a laser that's large enough and powerful enough, with enough shots, we can do what SLAC does. We can make a hard X-ray laser. And now, with a hard X-ray laser, you can do single molecular imaging. You can image proteins in vivo, not cryogenically frozen. Right now, we can only image about 200,000 proteins out of 200 million. We have AlphaFold, which is a wonderful AI mechanism. This is the prediction, this is the measurement on a cryomolecule. It's good, it's great, it gives a fantastic starting hypothesis for all kinds of research, but once you have that and once you work with that, you need to go and measure. And we can build a machine that can do that. And so now you have the whole wide pharma world as well. We're at UT Austin. We have lots of colleagues that have even more great ideas. So if you're more interested in energy materials, batteries, clean tech, advanced energies, quantum materials, superconductivity, there is somebody there who is infinitely more knowledgeable on those subjects than I am, and who thinks our machine would be a great addition to their tool set. And with that, thank you very much for your attention.